Passa. Você fez uma cena extra ali. Vai na primeira cena. Adiciona ela no pai, filha. Ele improvisou uma pinta com clips, eu achei incrível. Ah, é. Clips é sempre uma. Well, good morning, everyone. We are starting, like this is the last week that I'll be here. Then Andrea will arrive and assume the rest of the class. But we'll be seeing today and tomorrow things, concepts, and implementation of statistical modeling in R. And Thursday, I will talk about a few possible implementations of two-species dynamics and some other ecological things in R. So you can start prepare to the biology and ecology toolkit module. So today I'll be talking about some concepts in statistical modeling. I'll talk briefly about probability distributions, and then I will introduce you to the linear model. If this is like already super familiar to you, the idea here is to actually think about how we can connect theory and data using statistical modeling. So what I expect from today is that we can think about ecological questions and how we would translate that in a linear model or any model that we can think of. So a bit about concepts in statistical modeling. And this should be like an entire graduate course. So this is like super an overview of things, but things that are considered that are basal to understanding statistical modeling. And if you are comfortable with the concepts here, I think it's easy to navigate and build more complex models. Oh, something happened here. Shit. Deixa eu só ver se... toda a aula. Okay, something happened with the slides in the web page of. Huh? I don't know if I'm using the one that is on my computer, not on the web page. I'll fix. It's working. It's working now. Okay, great. Just took some time. So here are like basic references of this idea of connecting theory with statistical modeling. This book is like one of my favorites. This is The Ecological Detective, and the idea of this book is actually connecting theory with data, and it explores. It's a more conceptual book. It won't give you like it has tons of examples of statistical models, but it is not focused on that. The other ones are. And this one is from Bernhard and Anderson. And this is a super nice overview of model selection and multi-model inference, how we can confront multiple hypotheses. And those are like great references for connecting hypotheses with statistical modeling. And those are more hands-on books. This is from Benjamin Volker. He is an important person in ecological modeling. And he built a lot of packages, R packages, to do that. This is a super great book because it starts from understanding the data and probability distributions and then escalates to statistical modeling. And he actually like explains how maximum likelihood estimators works and things like that. It is a great tool to understand better how models work. As well as this one, this is like a more broad ecological statistics book. It has a lot of different people, different authors contributed to each chapter. Ben Volker wrote the mixed model chapter. And what I like about this book is that it starts from the linear model to explain all the other possibilities of statistical modeling. And that's the idea that I always had when I started thinking about this specific class. So this is like a super nice references to understand how to escalate from a simple concept to more complex ones. And there are like other statistical things that are important in ecology. Okay, but the thing is, we are talking about connecting theory and data and using statistical models to do that. And what we have to understand that we have to understand the data. We will always find what is the model that best explains or predicts our data, never the opposite. Okay, so data is the truth. And we want to explain, understand that truth behind the data. And a common concept in statistical modeling is that we search for a minimal suitable model. This does not mean that we are always searching for the simpler model, but the simpler model that fits well to our data. This is the concept behind it. And so we have to really understand the data and the concept so we can connect it. But about the data, we have to understand basic things such as the data distribution. And not only the distribution, but is your variable a continuous or a discrete variable? What is the nature of our data? If we have like sampling or an experiment, how many replicates do we have? How many independent observations do we have? What are the predictor variables, and what is the general pattern that we are trying to explain? And in order to connect data and theory, we build statistical models. And I put here two basic concepts behind statistical modeling, which are maximum likelihood and the principle of parsimony, the Occam's razor. So maximum likelihood is a concept, and there are different algorithms to estimate parameters based on this concept. But what I want you to understand here is the concept of maximum likelihood, which is basically that given the data, here I have like a data histogram of this is sample width from IRIS. Given the data, what are the parameter values that make the data most plausible? So I'm assuming that this follows a Gaussian distribution. It has two parameters, the standard deviation and the mean. So what are the parameter values that are closest to the data? This is what we want to find. This is what are the parameters that make the data more plausible here. So which is the mean that is closest to the mean of the data, which is the deviation that is closest to the deviation of the data. This is what we are looking for. and the principle of parsimony. So all things being equal, the simpler solution is the best. This is the basic idea here. So if I want to get from A to B, this is, if I'm using parsimony to choose which path I will take, doesn't matter that this path has more like a scenic view or whatever, but this makes me go from A to B faster, easier, it's faster. So given the two options, we would stick to the more simple one, but we are always searching for models with fewer possible parameters. In statistical modeling, I mean, we have like different areas like climate modeling. People want to predict like the weather forecast is an area that people use a lot of parameters because prediction is what we want. So we are not worried about like having models with tons of parameters in that case, but usually we should think about that because sometimes we can have like, here I have like 3 options of models feeding my data. This is like the predictor variable is time, and I have a response variable, the value of something. And in this case, I fit a linear model to this data. I would bet that this, if we do like an analysis, this could be significant because we have those data here and those data here, and this could like, we could actually have a significant result from this. But this is not a model that is close to our truth here, the data. So I can have a model with more parameters and build a curve like this curve. This would fit better my data, but I'm adding more parameters. I can add even more parameters and fit a curve like this. Okay, this fits really well to my data, but this is like an overfit. I don't need a model that is exactly my data. That's not why we build models. So if we want to describe the tendency, the pattern, something like this is better. So we are searching for models with fewer parameters. Linear models are preferable to nonlinear, but this is a case in which like this we have clearly a nonlinear relationship, so we need a nonlinear model here. Less assumptions, minimally adequate models, and simpler explanations. And here we always have to think that, okay, let's keep it simple, but at the same time, when we are talking about biology, ecology, or any area, if we need to describe a particular pattern, we need to understand what are the variables that biologically matter. So I cannot like leave out a variable that is like basal to the biological process that I'm studying. So fewer parameters, but we also have to be close to the reality that we are modeling. And this here is to sometimes we think that model, like the model is the real thing. And it's not. So the best model, if we're searching for the best model will be always just a model. And all models are wrong because models are representations of the reality. It's not the reality, it's wrong. So we do not have like the correct model. We are searching for the best model that fits my data. So imagine that the reality is kissing heart emoji. I could represent that reality using 2 different models here. Some models are better than others, right? But this does not mean that this is the correct model. This is the model that is closer to my data, okay, my reality. And we should always search for the simpler model, the better model, but we cannot be simplistic in terms of the systems, biological, ecological systems that we are trying to understand. Okay, so a bit about statistical distributions. Here, I'm talking about model and parameters and which model describes the data. When we are talking about models, we are always talking about a curve that has specific parameters. We need to understand really well the data. That's why we had like the exploratory data analysis class. But besides understanding like general patterns of the data, we need to understand what is the distribution that our data follows. And here, I'm bringing 4 examples. I have like 2 continuous variables, normal and not log normal. What I want to show you is that we can describe a statistical distribution based on the expectancy and the deviation of the distribution. And this will be always described by patterns of those distributions. So each distribution has their own patterns, parameters, and the parameters can be combined to describe the mean and the deviation of the distribution. So for the normal distribution, it's super straightforward because it has 2 parameters, the mean describing the mean and the deviation, standard deviation describing the deviation. It's a symmetric curve for continuous data. We have tons of examples in biological systems. It is very used when we have size distribution or any like measurement, continuous measurements of a variable. We have here 2 examples of discrete distributions, binomial, which is used to describe processes, binary processes such as presence or absence of species. We have Poisson distribution that describe independent events at a particular rate, and the rate is described by the lambda in the Poisson. And Poisson has only 1 parameter. The lambda is both the expectancy and the deviation. And it is used, for instance, for distribution of rare species in a community. And we have the log normal distribution. It is described by 2 parameters, the log of the mean and the log of the standard deviation. This is an asymmetric curve. When we have data about species abundances, we only have like 1 or 2 species. This is discrete, usually a Poisson or an inflated distribution with 0 inflation. But we can also measure abundance by biomass. And we do that, it's a continuous variable. And it will follow log normal distribution. So log normal distribution can be used for described abundance patterns, continuous abundance patterns. And the way we can generate, deal with distributions in R is using there's a lot of statistical functions that are already defined in R base. So the normal distribution is one of them. Here, I'm randomly generating a normal distribution containing 1,000 values with mean 0 and standard deviation 1. And I'm putting this result in a data frame, just because I will use ggplot and I will need a data frame for plotting. But here, I want to show you that we can use the R norm. This is for random generating a distribution based on particular patterns. This is the default, mean 0, standard deviation 1. Here, I'm generating a log normal distribution. I'm basically generating a normal distribution and taking the exponential function from that, because it's the log, so we are doing the opposite operation here. And this will give me a log normal distribution. We have R poised for generating Poisson data, R being for generating binomial data.
If we don't write the mean and the standard deviation,
It will, those are the default values. I'm writing just to show you what they are. Here, it will generate normal distribution with mean 0 and SD1, okay? This works for all R functions. If we do not specify a particular argument, it will use the default value, okay? We can check the default in the help of the function. So here are the distributions that are just generated. And in gray here, I have the data. So this is the randomly generated data. And in blue here, I have what is the empirical distribution that I would have if my data followed a normal distribution with mean 0 and standard deviation 1. Okay. Here. Oh, we have both.
On the last slide, it was written R norm, and here's D norm. Is there a difference?
Yes. Here, I'm showing the function that I'm using to plot this curve. So this is exactly what I wanted to show here. If I'm randomly generating numbers, I would use the R norm function. Here, the D norm function. Here, x, we do not have to fill that x with data. We are generating a normal distribution, the density curve of a normal distribution with mean 0 and standard deviation 1. That's what we are doing with the D norm function. This is creating a curve that would fit in data. I added here, this is a density histogram, and because of that, I can add this curve here and compare my data with the distribution. In the explanatory data analysis, there was an example checking the Poisson distribution, and there's a code for like randomly generating Poisson data, not randomly generating, but for creating a D-Poise curve based on the lambda parameters. And here is just for us to like observe when we think about a log normal distribution. This is what we need to imagine. This is an asymmetric curve, and here I'm plotting a density curve, like the exponential of that density curve. Okay, and let's go talk about the linear model. The linear model, we will assume that the response variable follows a normal distribution, and the errors also follow a normal distribution. But the thing here, we'll talk about the linear model. This is basically a mathematical model that describes like a curve with uncertainty. So we have A plus B, X plus the uncertainty. If we had just the mathematical model, we wouldn't have the uncertainty parameter. So this is another way of visualizing, representing the model.
Sorry, why you say that a normal distribution is a linear model or a linear regression? I don't.
I will go through that.
Okay.
But when we have a few assumptions to create a linear model. But the first one is that the response variable must follow normal distribution, and the residuals also must follow a normal distribution. I will explain what the residuals are, and it will make it clear. But we're talking about those variables having a linear relationship. So this should be more or less linear, so I can apply a linear model. If this is not linear, it's not, either I transform the data or use a different modeling approach. But we have to assume linearity between the relationship of these two variables. We have to assume that the error structure follows a normal distribution, and the response variable also follows a normal distribution. And here is just the relationship between the data. I can build here a curve to describe that relationship. This would be my statistical model here. And here I'm building a statistical model to predict what is the relationship between the predictor and the response variable. And when we are making predictions, we are making predictions only in the interval that the data exists. Because, I mean, I don't have data here like 2 point whatever and close to 10. I don't have a value here, but I can predict what the value would be, and that's exactly what we are doing with this curve. But when we are doing prediction, we don't go beyond the data. That's extrapolation. That's a different thing. So here is prediction, here is extrapolation. We go beyond the data. There are a few cases in ecology where we do actually extrapolate things. Usually we are doing prediction. We would stick to that only if you have like a really good reason for doing that. So the linear model is basically our mathematical model describing this curve with the error structure. And here we have to assume that the error distribution, the error component here, follows a normal distribution with mean 0 and the deviation of the data, okay? Another thing that we need to check is if our response variable is normal, and here I have the response variable in this example. And I could check that by creating a density curve for my distribution using the parameters of my data. So I'm taking here the mean of this data and the standard deviation of this data, building a density curve, and so I can compare it. I randomly generated this data, so this comes, I can guarantee that this comes from a normal distribution, but here we have a small sample size. That's why we are not really close to a normal distribution, but let's believe that we can stick to that and keep doing our model. And the other things that we have to understand what is the relationship between the predictor and the response variable. And we have to assume that this is linear. If this is not linear, we transform the data or use a different modeling approach. So those are the assumptions of a linear model. So the relationship between x and y should be linear. The residuals should follow a normal distribution. And there's a concept that is called almost elasticity, which means that the variance of the residuals is constant. If we go here, we have one parameter describing the variance of this residual, and this is constant through my model. We have to assume that. Sometimes we have curves, like I can plot a variable, and my data is almost here, but then I have something like this. This means that the variance increases with my predictor variable. We cannot fit a linear model to that because it doesn't follow the principle of the homogeneity of residuals variance. And we have to assume that the residuals error terms are independent. If not, that's why we use mixed models or other modeling approaches. Okay, so we have a statistical model, and our goal here is to estimate the parameters describing a particular curve. There are different ways of doing that. I'll talk about the least squares method, but maximum likelihood is highly used, especially in Bayesian analysis. Least squares method is it's a method very used in frequentist inference. And I'll go through that because I think it's a good way of understanding the residuals and the coefficient of the determination of the model as well. So I have here our two variables, the predictor and the response variable. This is their relationship. I want to find the curve that will represent this relationship. And the way that the least squares method works is that it will start from a particular position called the fulcrum. This is the mean of the predictor variable and the mean of the response variable. And from that point, we will create different curves, like all the possible curves that cross this point, and we will evaluate how far the curve is from the data. And the curve that is closest to the data is the curve that we will stick to it. So imagine that I create a curve like this. I will calculate the distance of every point to my curve. I'll compute that. This doesn't look like a good representation of my data. I can have a different curve. I will calculate all the distance from these points to my curve. I will check if this is good enough. And I will finally find a curve. This is the curve crossing the fulcrum point that has the closest distance from all data that we have. So this is how least squares method works to estimate the parameters. And this is how the LM function in R works. So if we want to create a linear model in R, I'm creating a model called mod here. This is the LM of my y1 tilde my x1. This is like how we express a relationship in R. And this is the notation that we need to use for a linear model and for like all the others as well. And if we apply the function summary to our object, remember that we use it a lot, the summary function. When we apply that to a vector, for instance, we have like the momentum of the distribution, the minimum, the maximum, the mean, and like basic descriptive statistics of that vector. And because R is an object oriented language and objects have classes, we can have this type of behavior. So when we apply a summary to a vector, we have a particular result. When we apply summary to an object that is a linear model, so the class of this object is a linear model, the outcome will be different because the summary function is checking the class of the object, and it will choose a different method depending on the class of the object. So this is why we can do this. So we have here the formula that we use it in our model. So it will show, remember us, what is the model that we are building. It will show us the residual distribution, the minimum, the maximum, the median. It will show us the coefficients of our model, the intercept and the slope here. It will give us a p-value, but the most important thing to check when we do a linear model is not the significance codes, but the estimate of the parameters. This is what we are interested in. Ben Bolker, in his packages, he removed the significance test from the summary of the model visualization because he defends that we should be worried about the effect size, and the effect size, we can tell that based on our estimate and the confidence interval of that estimate. So we should really be worried about the parameters, more worried about the parameters in the model than the significance of that. And another thing that I want to show you is that it gives us a multiple R squared. This is the coefficient of the determination of our model. It basically tells us how much of the variance of the data is being explained by the model. Okay. So we have all this summary here, but we can extract particular parts of our linear model using other functions. So we wanted to find the intercept and the slope of our model, the A and B. Here in statistics, we always use alpha and beta for those parameters. So the intercept here is 1.63. This is what we found out. And the slope is 4.08. And plus our error structure. So when we are looking at the effect size, we should care about the coefficient values and the confidence interval of those estimates, because sometimes like we have a super high coefficient showing a super steep curve, positive curve for instance, but when we look at the confidence interval, it can go from like, it has a huge variation compared to the mean. So it's another important part of statistical modeling, understanding the confidence interval of the estimates that we are doing. And we can do that by applying the confint function to our linear model object. Linear models have like everything on R base. If we are dealing with more complex linear models, we have to estimate the confidence interval using like more complicated procedures, but for linear models this is super straightforward. And the residual. The residual is basically the distance between every data point to the curve, the predicted curve from our model. This is the definition of the residuals. And based on that, we can partition it. The residual is a measure of how distant my data is from the curve. We can partition it, that variance, into different components. That's what we are doing. So for linear models, this is super straightforward. For mixed models, it's a bit more complicated, but it's been a few. When I started my PhD, we didn't have a way of doing variance partitioning for mixed models in R. You were like in, I don't know how old you were, but right now there are different packages that can do that because it has like a more complex structure. But it's by the end of my PhD, I had a tool to do that, and that was like crucial for my main question. So I'm glad that the community developed a solution on time, right on time. Okay, but we are talking about variance partitioning, and this is how we define the sum of squares. This is SS, what this SS stands for, from the linear model. And this is basically, the variance is on two different components. The model component that is here as the between component, and the error component, okay? This is where the variance is in our model. So we can calculate the total sum of squares by, this is the formula for doing that, and this is the graphic representation of what we would do here. So the total sum of squares is basically the difference between every data point, every yi point, from the mean value of the response variable, the squared difference, and we sum all of those components. And here, and we can actually like calculate this by hand. We take those values, we take the mean, we make this operation, squared that, and sum. And this is what we calculated by hand. This is like the total variance explained by our model is 450. We can calculate the residual sum of squares, and we do that since the residuals are the distance between the data to the predicted curve, the way we do that now is comparing every data to the expectancy for that data. And we square that, sum that, and we get like 200. With that, we can calculate the other component, the model variance that is missing here. This is very basic algebra, and here we can calculate the model sum of squares. So the total variance in our model is 450. The error variance is explained by the error component is 200, and this is what is being explained by our model. If we look into those numbers,
I have a question. I didn't get it. What's the difference between the two sums of squares?
okay, we are talking about different components. This is the total, the first one. The total is given by this definition. So this is the total variance being explained by the model, basically. Including the two components that we have, the fixed effect being the response variable and the error structure. Remember that our model is given by this relationship, y equals alpha plus beta x plus our error. We have the total variance here. In our case, this is 450, the total sum of squares. We can calculate the total. We can calculate the error. This is 200. So the rest is from this part, the other 250. And this gives us the idea of how our predictor variable is good in predicting our data. Here, basically, our variable and the error structure are almost equally explaining our data. And we will see that we can do variance partitioning R using the ANOVA function. We can apply that function to our model, and we will have exactly that. So the sum of squares of the model component, the sum of squares of the residual component. This is exactly what we did by hand. We don't have to do that by hand, but that I wanted to show you how we can calculate that so we can better understand and visualize that. And the coefficient of determination, the R squared, it is basically the proportion of the variance being explained by our data. So this is the 250 here, 249 divided by the 450, and this is 55%. So this is not a really good model because it explains only 55% of the variance in our data. We should have a majority value here, above 70%. But in ecology, it's super common to publish a paper with 55% is more than 50, so it's good enough. But again, the important thing here is the parameter estimations and how and the confidence interval of those estimates and how the model fits the data. So this is a really, this is how we should evaluate first the model. We need to think about how this fits the data and how the parameters that we are estimating are good enough for doing that and the biological meaning of that. And okay, we can show a p-value and a coefficient of determination, but the most important part here is the focus on the effect more than the okay.
If the R squared is related to the correlation coefficient R, the R-squared is related to the
Correlation?
related to the correlation.
To the correlation coefficient.
R.
Those are different measurements of the relationship between two variables. The R-squared I mean, in terms of the evidence, it would be related, but it is telling totally different things. So when we calculate a correlation between the two variables, we just want to know how close to the linear relationship they are. We are not actually creating a model and estimating parameters. We just want to know how close to a linear relationship they are. And the R-squared is a measure of how much of the variance is being explained by our model. So yes, they would be related, but they assume they serve different purposes. Okay, our coefficient of determination. So let's go to the tutorial because I want to show you at least how we can, after doing a model, how we can do the diagnosis of the model visually in R. So we will go back to here. I'll do exactly as you will do. We can go to the statistical modeling module. We have a tutorial here. And it has much more explanation. Oh, I'll start with the tutorial first because I want to talk to you about the context before. So there's another book. It's on the references list for this class. That is the R book written by Michael Crowley. And it's a really, really good book about teaching basic statistics. And the part of the linear model is really, really good. And it's actually used to teach statistics with R code together. So it's very, very useful. He makes a lot of choices that in terms of workflows and good practices in R are questionable, but the statistical content is amazing, so check that. So I'm taking an example that he has in the book, and it's data about growth of caterpillars that were given different diet with different tannin content. And tannins is really good in wine, but for the plants, they defend leaves against insects. Most evidence of this relationship, this plant herbivore relationship mediated by tannin, comes from correlational studies. And what they did is that they did an experiment, given different quantities of tannins to caterpillars and measured the result in terms of the growth of the caterpillar. So the question here is, do leaf chemical compounds affect the growth of caterpillars? So we have a research question. So how do we start doing models? We have to have a question first. I'll just do this. Okay. So here is our question. Here is the a bit more on the context. There's a review paper on this herbivore relationship. So we start with our research question, and then I mean, we have our question, we have the theoretical context, which is that tannin compounds can defend the leaves against herbivorous insects. And we can think about an hypothesis for that. So our hypothesis here is that the toxicity of the tannin in the leaf reduces the growth of caterpillars. And we can even make a prediction from that hypothesis. And our prediction here is that caterpillars that consume leaves with greater amount of tannin will grow less. I want you now, a volunteer, to graphically represent the relationship that we are predicting here. So what is on my x-axis? Tannin. So basically the quantity of tannin, and my y-axis? Growth. Okay. I need a volunteer to draw here a curve representing our prediction. It goes up, it goes down, it goes in what direction? Come here, I cannot. Sebastian.
It will be like this.
Perfect. So yes, this is exactly what we are predicting. And this is what, like, we want to create a model, we want to find what are the parameters of this curve. This is what we will do. So this structure is always like, this is a really simple example. We only have one predictor variable, one response variable. It's super straightforward. But the idea here is that if we start from a question, we have a hypothesis, we have a prediction for that hypothesis, we can graphically represent that. And that's what it means, like connecting theory with data using statistical models. This is the exact meaning of that. Glauco Machado will teach you like hypothesis-driven course, and he will work with that structure with you. But for like statistical modeling, I really like to stick to this structure. Sometimes we do not have like a clear prediction. We are just exploring relationship between variables. So this is more like variable selection than hypothesis testing. Sometimes we do that, and we do that a lot in ecology. But even though we do not have explicit prediction, we are doing exploratory thing, we should be able to think about the possible outcomes of the relationship of the variables that we are exploring. So they did an experiment on caterpillar growth, varying the tannin quantity. And the first thing that we want to check is how, okay, let's start doing that on R. Now we can go to R. So we have here, you can find here the R code for the tutorial. I will do how I was doing in other times. I will go to my repository. I will open my R project. I don't want to do anything. I will paste the script here. I will save that on my R folder. Do not forget to choose the R folder here. I'll call this 5lm.r, and I will save here. Now on Git, I have this script that is not being tracked by Git yet. And you also, or I would need also, to download here the data. So I can download here. It downloaded the data here. I'll go to my downloads folder. I'll get this. I'll add this to my data raw folder. And here now, inside my project, I have my R script and the data that we will use. So this is from the Crowley book, and the file is the regression CSV. I will load ggplot2 because we will use that too. And I will start reading the data. I'm calling the data cat because of caterpillar, but there's an R function called cat. I should not do that, actually. But okay. So we have our question, that is, do the leaf chemical compounds affect the growth of caterpillars? I'm going fast, I don't know. Are you good? Like, you found the script, you found the data? Okay. So I loaded my data into R. I can check that. Cat. Data is just growth and tanning. And I want to check how the distribution of my response variable is. The closest to a normal distribution, the more symmetric the box sizes are here. We do not have outliers. We have a more or less normal distribution. And our predictor variable, I'm showing here just the unique values that we have. So it's 0, 1, 2, 3 in whatever quantity it is, but it's the different amount of tannins that the caterpillars ate. And for creating our linear model in R, we are using the LM function. And we want to create a linear model of the growth in respect to the tannin. So we use the tilde here for that. And the data that we want to, where those columns exist, is the cat here. So I have now an object called mod catch. It will show me the formula of the model that I created and the estimated coefficients. Here I'm just like checking what is in my mod cat. If I check the class of this object, mod cat, this is a linear model. So we have a specific class for linear models in R. I'm just showing you that. And I can do a summary, and it will show me a little bit more of what we saw in our model. It will show us the distribution of the residuals, the estimate of the coefficients, and our multiple R squared, which is like 0.81. And if I want to plot that relationship, I want to plot that model, I can plot first my variables here. I will add here one more argument, which is called las equals 1, so that my numbers are horizontal now. So this is the relationship between tannin and growth. And for plotting the curve, one option is to use the function AB line, because it's a function that plots a linear curve using A and B parameters. And again, because mod cat is a linear model, when we apply the function AB line to this model, it will extract the coefficients and use the coefficients as my A and B arguments. So if I do this, I have this curve. This is the exact, let me show you how we could do that. Like, we can assess the coefficients of the model using the coef function. So my A here, my intercept is my coef of mod cat 1, and B is this, 2. And I could simply add A equals A, B equals B. And I'll plot this flow. I'll make again the plot, and I'll plot this. This is exact the same. So, but I do not need to create an object with the coefficients, because this function, AB line, works with an object of the class LM. That's why we can do that. We can do the same plot on ggplot, and the way we do that is we specify what we are going to plot, our data, and the aesthetics showing our x and y variables. What are those variables? I want to plot only points, so this is what I get here. And I can add the curve from our model by using the function geom_smooth. And I have to tell that my method here is a linear model. And then if I do this, I would have this curve here. And I'm just changing the theme because I cannot deal with the gray background. And note that it already plots the confidence interval of the predicted values. We can change that, like there's a C, I guess, equals false. I'll have this. It's great to have this. If I do not specify the method here, it will create a smooth model. So this is not this is the default, okay? So, and this is not the model that we fit. So if I want to see the actual model that we want. And we can specify different methods here. We can specify different formulas if we have a more complex model structure as well. So it's super useful, but this is just to show how we will do the same thing that we did. I do not use this line here. Here using base, and here using ggplot. And we can check the variance partitioning of our model using the our ANOVA table. So we can use either the ANOVA function or this other function, summary AOV. So this is our analysis of variance. It will show us this sum of squared of our model and the residuals. So here is why we have a high coefficient of determination, because the amount of variance being explained by the model is 4 times higher than the variance explained by the residuals. I think we have a question, Lucas?
My question is, I remember that there's a specific function that we can see the data that R is using to build the graph. Do you know what it is? Because, for example, if I use another smooth method, I want to see how he's calculating
okay,
this.
okay. There's an argument, geom smooth. Let me search for formula. Okay, there's an argument called formula. And it's where we would specify let me see if we have an example here. Okay, here. Here there's an example. So we have this data, and probably the person is building a model which is not like the exactly linear relationship between those variables and MPG. So it's an LM, but you can specify, like the data is the MPG. So we do not have to check that, but we can check, like we can specify what formula we want to use to build. So it's 2 things that we need to specify, the method and the formula that we can specify. In our case, I'm specifying the method, and the formula, I'm just assuming, like here, it will show me a message, like geom_smooth is using formula Y in relation to X. So this is the default, and that's why I'm not specifying the formula. But
Okay.
if I want a different formula for my model, for the model that I'm plotting, I can do this.
Okay.
Okay?
Mhm.
Can we obtain like a summary from the ggplot linear model? I mean,
Oh, okay. So that's why I don't like this specific functionality from ggplot. I already had students coming to me. I need to plot a linear model, and I cannot do this, but I found this, and like the person like fit a linear model, but the person doesn't know like why. And so the model, I like to use this function to build a model that I already created. We should not like be creating the model inside ggplot. That's not why ggplot exists. It's a grammar graphic. It should be used for graphic purposes, but it has this functionality to do things for us. So I do not need to specify to create an object with my model and use that on a B-line. I can simply use geom_smooth and specify which model I want. But we should not like start doing this before thinking about what is our research question. What is the model structure that we would create the model, check the coefficients, and then plot. So this is not like something that we would do like by reverse. This is really good for visualization, for exploring things, but the model, what dictates the model is our hypothesis, okay? Another thing that we can extract, and this is like all these functions are on our base. So when we install R, we already have these functions. Tomorrow, like for GLM, for generalized linear models, we also have functions on base, but tomorrow we'll be installing other packages to create other model structures as well. But here we are using R-based functions to create and explore the outcomes of our model. So ggplot is great for visualization, but the model we should build like explicitly create an object with our model and inspect that. Another thing that we can extract from our model, and so see that I'm applying the function to our object, and it will return the predicted values. So what would be the predicted values when I'm giving one, not one tanning, but something in one quantity of tanning, and what would be the predicted size of the caterpillar. And we do that by extracting the predicted variables here. I'm here just applying, I'm creating now a column in my data called fitted with the results from the predicted model. So cat, now my object, cat has this fitted column, and I'm using that on ggplot to recreate the line predicted by our model. So how we do that? So let me compare. Okay, so what, I'm not doing that. I'm just, I'm comparing the fitted and observed values. So I have my growth, my observed value, and my fitted values here. And what we want is that our observed values be super close to the fitted values. So I'm creating here a line with slope 1 and intercept 0. And let's remove this background. And what we expect here, like if the model is really well fitted to the data, we would expect all the points really close to this line that I'm drawing here. But this is like I'm checking something by hand. In RBase, deals really well with this model object. And if we plot that model, it will show us 4 plots that are super useful for model diagnosis. I'm creating here, let's see if this will work. Okay, great. So I'm creating here a panel with 2 rows and 2 columns, and I'm adding here, I'm plotting the model, and I will have 4 different plots here. Let me give it a zoom here. Okay. So there are different things that we can check using this plot. This plot basically checks the assumptions of the linear model. So the first one, for instance, we are checking if the residuals are close to our fitted values, and what we should expect here is a horizontal curve, like this red curve should be horizontal, and we shouldn't see, this is checking the homogeneity of the variance, and we shouldn't see like any pattern here. We should see like data that is like spread across the panel like equally without exhibiting a particular pattern. So like any pattern like this, or like a U curve or a bell curve or whatever, any pattern is not desirable here because we want to know that residuals are homogeneously distributed. The normal QQ plot. The numbers here are indicating the position of the values. Not this. It's not the position. It's either the position or the actual value that we have, like in the growth, like the fitted value, the actual value that we have. I will check that, but it's either the fitted value. No, not the fitted value, no. Here is the fitted value. The 7. Yeah, it is the fitted, but it's on a different, why is 7 over there? That's what I'm trying to figure out. It should be, okay, probably the position. Yes, that's why this is 4 to 6. This is the position of the data in our, so that way we can identify what value is that one, is in the row 7 of my data frame. The normal QQ plot, it will show us if the residuals follow a normal distribution. So we are comparing the theoretical quantiles of a normal distribution with the standardized residuals. We should expect all residuals close to the dashed line here. This plot will show us, again, this is the plot that will show us how the variance of the residuals is distributed. We should expect here a horizontal line again, and not like here we have one point that is making this curve going down, like these 2 points. So this is not something like desirable. So this is deviating from our expectancy. So this curve shows us how the variance is distributed. And here is like, there's a measurement of how, again, how big is the variance from the residuals, and it's called Cook's distance. And we standardize the residuals and we calculate the leverage, and what we expect here is all data within the interval from 0.2 to 2, like anything higher than 3 is a distance that is too far from our expectation.
I have a question here because all these assumptions we are like kind of reviewing, but only visual, right? And if, for example, I know that if I want to see if my data follows a normal distribution, I could just apply a Shapiro test, right? But or which other methods, for example, just to not only visualize that the assumptions are accomplished.
Okay, so here we are inspecting basically the residuals of our model, not the distribution from the data. It will affect like how we build our linear model as well. But we already know that our data follows a normal distribution, and that's why we are doing this. And we are doing this to check if our model is a good model, because if the residuals do not follow a normal distribution, it is because we do not have a good model. The model is not good enough to describe our data. And previously, there's like in the end of the tutorial, there's a few exercises using a package called FitDist Plus. It's a package that you can use to check first, before building your model, what is the distribution of your data, and then we use that like to choose like what kind of model we would build. But those are like tests that we do like after fitting a model to see if we do not have like any strange residuals distribution or like pattern that will affect how good our model is to predict our data.
Yes, my question is that if we can measure the residuals follow a normal distribution with a quantitative test instead of visualizing only.
Okay, we can, yes. It depends on how you want to do your statistical inference, really on that. I like understanding really well my data, doing that previously, and if I do need to choose between gamma or Weibull log normal distribution, I could do a test for that, but it doesn't exclude the need of doing this, okay? But yes, we can do tests. There are different tests for like checking if the distribution fits the data or if your residual is normal distributed. But again, I do not think that statistical tests exclude like any inspection. We can do like both of them, but you do not need like a test. Like if you can easily see, like sometimes you do not even need a test, but you can do a test for that. There are tons of like goodness of fit tests that you can use for that.
If I made this, I use this package and I discovered that this kind of distribution, like a normal distribution, but this plot here show me problems. What I do?
You sit and cry. No, I'm just kidding. There are different things that you can do. Like first things that like we need to make sure that our response variable follows a particular distribution, and we are representing that in our model. If that is not what is incorrect, we should think about the model structure. So we are probably not using the variables or not specifying the variables. Like we can have additive effects, interactive effects of predictor variables. So sometimes like we need to review the model structure. That implies like sometimes like reviewing our hypothesis, but sometimes it is just like different ways of translating your hypothesis into a model. But that's why the exercise of thinking the hypothesis and thinking the structure before the analysis is super important, because we need to make sure that like we are testing what we want to. And sometimes it's super common in ecology to find like something like this and it's not working. Sometimes we need to like choose a different method, like a linear model is not working. or you need like a more complex model structure, you need probably an error structure that you are not accounting for, so you can use a mixed model. You can change the type of the model structure in different ways, not only by changing the predictor variables, but you can add a different error structure. Usually, when we do that and we have like a weird residual pattern, probably the best way of dealing with that without like changing the hypothesis or changing like what you are doing is thinking about a different error structure. So our error structure in a linear model assume that your residuals follow a normal distribution with mean 0. And sometimes that is not true. So we can think about like if you have, like if we have the means like for doing that, like sometimes here, imagine that I have caterpillars that are like from 2 different generations, for instance, whatever. So I can add another effect, like I want to control for the generation of the caterpillar, but I'm not interested in the variation between generations. Like I want to like understand the general. I still have the same question, but I do need to model like an error structure in a different way. Yeah, I will talk more about that like tomorrow. I have an example that starts exactly like this. Like I'm starting a linear model and I will inspect the model and I will see that like this is not like a really, I'm not following the assumptions of the linear model, so I'll change how we are building the model. But we should do that exercise in advance, and sometimes like ecological data, biological data is really tricky. So sometimes data transformation or changing the model structure, especially adding an error structure that is not simply assuming that there are errors follow a normal distribution.
I don't know recommended, but before, like in my class, we used to make some transformations to the variables so they fit the assumptions. Like we changed maybe the response variable or the factors. We are transforming it like an exponential or logarithm.
Yeah.
So it worked.
But that is related like to what we should do before. Like we should find before like the distribution of the data. We can either change the type of model that we are using. It's not a linear model. It will be a generalized linear model using a different distribution, or transform the data. So sometimes transforming the data is enough. Sometimes we have to think about other ways of doing that. Okay. I want to show like really if you will need to install this package, FitGist3+. I'm loading the data here. This is ground beef serving size data set. It is ground beef serving size in French in a French survey, and basically this is a data frame with the serving here. It's serving size in grams. It's what children in French were eating. And I can do like a histogram with that data. Ground beef serving. So this is the data that we have. And I do not know what the distribution I should use. So this package comes with different functions to explore different distributions. The first one is this one. So this is our data, and this is the empirical density of our data. This is a curve built from the data, not assuming any particular distribution. And this is the cumulative distribution of my data. This is another way of visualizing this same histogram, okay? And okay, we can do that just to inspect the distribution. There's another function. There are other parameters besides like the mean and the deviation of the distribution. And two parameters that are super important is the skewness, is how much like our data is has this long curve, and the kurtosis. And those two parameters are good ways of like understanding that we need an asymmetric distribution, that a normal distribution is not good enough. So this is continuous data, and it's showing me that it has this value of skewness, and we should think about fitting a distribution that can deal with skewness, which a normal distribution cannot. So I can fit a distribution to my data using the fit dist function. It has in the package the most common distributions implemented, but not all of them. So I'm creating an object here, and it will give me the parameters of the distribution, the shape and scale, which are the parameters of the Weibull distribution. If I check this summary, I will have a bit more information than that, and it will give me the likelihood of this, how likelihood measure is a measure of how close to your data the function is. So we can compare different fits using an information criteria, which will use the likelihood and will penalize for the number of parameters.
Okay, so I didn't get it. Like, it's going to assign any distribution, like
no,
any.
I'm choosing.
Okay.
Weibull.
Okay.
I have to specify the distribution. You have to inform. We have to always think like what are the possible distributions, and then we test. Okay, it's not like something that we do like, oh, let's test all of the distributions. I'm comparing here distributions, skewed distributions, skewed continuous distributions. So I have those three possibilities. It could be a Weibull, it could be a gamma, it could be a log normal. So I want to check which one is the best to describe my data.
And like, should we do it like, we are going to test, I'm going to test the distribution. Can I just test it and see like, okay, that's better, so I'm going to use that? Or do you think that like, we should like analyze the data first and then?
No. What drives the decision of what distributions to use here is the nature of your data. If you have continuous data, you should pick a continuous distribution. You have a continuous data that is asymmetric. You cannot use a normal distribution. We will choose a different one. That's why I'm talking about statistical distributions in this class, because we need to understand the nature of the data, and there are different statistical distributions to describe different processes. So the distribution, like if we think about abundance data is naturally a Poisson distribution because it's a discrete variable describing an event, the abundance, the number of abundance. So it will depend. Sometimes the Poisson distribution is not enough because abundance data is super zero inflated. So we need to use another distribution, but it will be a discrete distribution that can deal with zero inflation. So what distributions we should choose, it depends on the nature of the data. That's why we need to know the data and know about statistical distributions. We do not do like statistical modeling without going back to the statistical distribution class, okay? In the Ben Boker's book, there's a really good chapter about statistical distributions. And yeah, at least that book has a really good, but it will depend on the nature of the data. So we have here a continuous variable, and we need to deal with the skewness of this variable. So I'm fitting a Weibull distribution, and I can check that. I'm also fitting a gamma and an log normal distribution. So I'm creating FW is my fit to a y-bar distribution, my fit to a gamma distribution, and my fit to a log normal distribution. I can compare those fits by the density curve or the quantile curve or the cumulative distribution function curve or other options here. I will create here. So here, I really like histograms and the distributions. I think it's easier to see. Let me, I'll go back to one panel only. This is only to show in row 1, 1. And I will plot only the first one. So this is showing me the different, how the different distributions are fitting to my data. So I have here a y-bar in red, a gamma in blue, and a log normal in green. And I can visually inspect what would be best. Like, none of them are actually capturing everything, but some of them are better in capturing what my data is. And there's a function here for those of you who love tests. There's a function here, goodness, different goodness of fit statistics, and we can compare the different distributions. All of those measures, tests, Kolmogorov, Kramer, Von, Anderson, Darling, they are parametric tests that will depend on the number of the parameters of the distributions, and we should not use them when we are comparing distributions that have, for instance, different number of parameters, because they are, we cannot evaluate overfit with those tests. And for comparing different distributions, information criterion, which are criteria based on maximum likelihood principle, it will tell us how close to the data our distribution is. And the rule here is to take the lowest value. So here, the gamma distribution would be the one that, like if we are using the Akai criteria, for instance, the gamma distribution would be the one that fits better to our data. The same with the BIC. It's similar criterion as Akai, but it's used for Bayesian inference. And if we see our plot here, like the log normal seems a really good fit because it goes like on the top of our density, but it is to the deviation. It's not predicting well all the deviation in my data. So that's probably why it is telling us that the gamma distribution is better, because, okay, it does not go all that way up, but it has higher standard deviation here. The shape of the distribution fits better to my data. So this is how we could do this. But again, I would not check if this follows a Poisson distribution, because it's not the nature of this data. This is continuous data, skewed data, and I'm comparing only skewed distributions that can predict that skewness. And that's basically it for today. The tutorial has more information, like the code is only the code, but the tutorial is here. And there are here like the books that I mentioned today, plus Crowley book, the Fitch dist package, and other books that are really good for understanding the concepts of ecological statistics and statistical modeling. And like in R, like this is a more recent package called TIDE models. And Julia Silge, one of the authors of this package, she works a lot with machine learning and modeling in that context. But this TIDE model package is a super powerful tool to build any type of model, even linear models. So we can do that. Like Andrea will use TIDE models in the predictive analysis class, but I wanted to use like the base so we can know that we do not need any fancy package to create a simple linear model in R, as long as we can create a linear model because our data and the residuals follows the assumptions of a linear model. So that's it, and I'll see you tomorrow, okay? Ah, my God, that was almost, okay, I will do that because you won't let me leave here without my commit of the day. Okay, I will get, those of you who are like I don't know who, oh, maybe Kawe, who is not here. He was having problem, he didn't want to use RStudio, but we don't need RStudio to use Git or any other like fancy stuff. We can do that using only the terminal. So if you have terminal and a remote repository, you can work with Git. You don't need anything else. I will add my script. Ooh, I'm not doing this right. Git add my data. I want to have my data here as well. And I will git commit message, adding script. Told me to.
Sara, will there be a Q&A this afternoon?
Huh?
Will you be available this afternoon?
Yes,
too?
I'll be there. I'll be in the office 109 until 4. After 4, I can meet you in the room. Some of you already signed up for that, so I'll respect the order from the names in the document. But yes, git add and then git push. And now I'm free to go. I have nothing here. Okay. Oh, I always do that.